Now, if you are most people, you would actually choose option A. In that, what we want to do is be able to lock in that certainty. Certainly we see the appeal of $1,000, but is $1,000 at risk? And the risk is, yes, half of the time we may get it, but half of the time we may not. So the certainty of $500 is viewed as more appealing than the uncertainty of possibly winning $1,000, but at the same time, possibly winning nothing. Now that presents a dimension, but only a dimension of how decisions work. Now it's an interesting one, because if you were to look at classical economics and you were to look at these two choices, they would say, well, the expected value of option A is $500. We take the probability and we multiply that by the value to be able to say what is the relative value of that choice. Now, the total value, we've got to add that to $1,000 we've already got, so it's $1,500, but in terms of this option, the expected value of this option is $500. If we look at option B, the expected value of that is exactly the same. So theoretically speaking, if we were to actually accept classical economics as a base, we shouldn't care which of these choices we make. We should actually see a relatively even distribution of, if we were to ask an audience sitting in a room, half of the people in the room saying option A, half of the people saying option B, because for the most part, they should be valued the same. So given that there should be no inherent preference one way or the other, the distribution should be even. In reality, it doesn't work that way. When experiments are actually run, 80% of the time people choose option A. They want to lock in the positive gain, and they're not